Welcome to this video, and in this video I wanted to have a look at a very interesting system. So the main system is a quad star system, so there's four stars all orbiting themselves in some configuration, but then there's a fifth object, and it could be a planet, could be a substellar object like a brown dwarf, could be a star, and it's called 30 Ari Bb. I'm going to have a look at that in this particular video and then decide or work out what it actually is. So before we get started, it's worth noting that planets orbiting more than one star are not particularly rare. It's quite common actually, and you can find lots of planets orbiting double stars, binary systems like this here. They might be going around the outside. They're a little bit more stable than ones that are orbiting one of the stars and then the two stars orbit each other. So we know that lots of planets orbit more than one star. Some actually even orbit three stars. So let's say we had a binary system in the center, we had a third star going around the outside of those, and then we had a planet orbiting around that third star. Again, there are a few planets, and it's not just one, there are quite a few actually that do orbit three stars. And we could potentially have planets orbiting four. So in another video, I mentioned a planet that was orbiting four stars. And this could be the case with this one here, this 30 Ari Bb. So this is the system. This is 30 Ari, and it is a quad star system. And it has an A and a B component, which actually orbit around a common center of mass. Now, the object, this fifth object in the system, was detected in 2009, and it was thought to have a mass of about 10 times that of Jupiter. Now, I say it was thought to have a mass. The way it was detected means that is a minimum mass, because we don't know the configuration, because it was a radial velocity measurement. So we can only get a minimum measurement, and that was, it had to be a minimum of about 10 times the mass of Jupiter, and that was detected 2009. So this fifth object there that we weren't entirely sure what it was, but it was there nonetheless, and that was orbiting the B component, the B binary system there. So let's have a look at the actual system itself. So the actual stellar system here is, so the A component is a binary, and it has an F type and a red dwarf for orbiting their common center of mass, and it takes just over 1 day for them to orbit their common center of mass in their own little system there. So F type is not that dissimilar to the sun, so it's around that sort of solar type, and a red dwarf is obviously much smaller. They're cooler, so they're going to be red. So these are quite close to each other with a very short orbital period. The B component is almost the same sort of configuration. It's an F-type star and a red dwarf. So it's a bigger star and a smaller star. They're a bit further separated this time around, and they have an orbital period of about 80 years. So much further apart than the A binary system. Now the actual A and B components, the A and B binaries, they orbit a common center of mass, which is in the middle of the two there. I've not marked it here, but it's in the middle of the blue arrows of that circle basically there. And as they go round, it takes about 34,000 years for them to orbit their common center of mass. And then they're obviously orbiting themselves in their own little system as well. So this is the main stellar system for the 30 Ari system. Now, again, I said that it was detected in 2009, but it was detected with the radial velocity method. And again, that has some constraints on what you can actually find. So you can calculate the mass of the object here. And what they did was they found that it was actually orbiting on the B, the bigger star of the B binary. So the F type, it was found to be orbiting that one. And it was originally thought that it could be a massive planet or a brown dwarf. Because of that mass, that minimum mass, it's kind of in the range of being a massive planet. It could potentially be a brown dwarf. The brown dwarfs are like a category between massive planets and low mass stars. They're not generating energy in their cores like a low mass star would be, but they're kind of not quite a planet either. So they're kind of substellar. So it was originally thought it was one of these two when it was first found. So when it was first found, it was found due to the wobble of this larger star. So what you do is you look at the star, and as it moves away from us and towards us, you can get the Doppler effect. as that planet orbits around the star, well, I say orbits the star and the planet actually orbit a common center of mass. And because of that, the star can be seen to have a bit of a wobble. So it moves away from us and towards us. And we can measure that Doppler shift, which is what this plot is here. So we measure the actual velocity of that towards us, away from us. We get that wobble. And from that, you can work out the mass of it, or a minimum mass, I should say, because you don't know the actual inclination. And you can get the orbital period. So what I've marked on the plot here is the orbital period. So from peak velocity to peak velocity, it's about 335 days. So the orbital period of this planet is a little bit less than one Earth year, basically, around this larger star in the binary system. So again, just to kind of give you an illustration, really, is when you use the radial velocity method, we don't know the inclination of the orbit. It's not known because we don't know how inclined it is, line of sight. So we always have to note that it's a minimum mass, because actually, if it is completely edge on, we're going to measure a maximum velocity there and we can get the mass quite accurately. But if it's much further inclined, has a high inclination, then line of sight wise, we're only getting part of its movement. And that means that the mass will be very inaccurate. So because we don't know what the inclination is, we have to always write it as a minimum mass. So in 2020, Gaia astrometry measurements were able to determine the inclination. So astrometry means that you're looking at the precise, or the positional measurement of the star in space. So you can actually watch it wobble in a different direction as opposed to being line of sight. And because of that, you can then get the inclination of its orbit. And that was able to more accurately constrain the mass of this fifth object in this system. Now, unfortunately, what that meant was the mass was a lot greater than it had originally been thought. So it actually turned out to be almost 150 times the mass of Jupiter. Now, because of that, it places it in the range of a red dwarf. So actually, this fifth object was a star. It's a very low mass star. You've got like 3 red dwarfs in that system now. And you end up with this 5-star system as opposed to it being a quad star system with a planet orbiting one of them. So whilst it's not interesting with regards to planets, 5 stars in this configuration is quite exciting. How do they get there? How do they even form? Because to get in this configuration, there's a lot of dynamics occurring there. So it is an interesting system nonetheless, but it's not for planets. So thank you for watching, and if you enjoy, then check out some of the other videos.